Good morning, good afternoon, good evening. We are back and better than ever. The last time we were together, we discussed lines in 2D, and now we're going to discuss lines in 3D or 3 dimensions. In 3D, we are dealing with a line in space. And just a quick preview. Here is an x-axis, a y-axis, and a z-axis, and this green thing is a line. This right here is the plane formed by the y-axis and the z-axis, and it just shows you where the line is going through that axis. So you can kind of get an idea of what it might look like. Very similar to what we're talking about in 2 space. Remember, in 2 space, we just had x, y, a1, a2, t, and b1, b2. This is still of the form r equals a plus t, b. What's r? R represents any point on the line that has and any point on the line is going to have an x coordinate, y coordinate, and z coordinate. A represents a fixed point on the line, a point that we know is on the line for sure. And B is the directional vector that tells us the direction of the line, and T is a parameter. Okay, and that's all that this says right here. In 3 space, we do not talk about the gradient or the slope of a line. We just describe its direction. We couldn't talk about the gradient. It's not possible. Okay, and so the parametric equations of this guy, let me get rid of the R, A, and B there. The parametric equations of the line are x equals a1 plus t times b1, y equals a2 plus t times b2, and z equals a3 plus t times b3. And each of the points corresponds to exactly one value of t. We can't mix up these t's when we're talking about a particular point. And t is a real number, it's just called a parameter. And then there's the neat picture of the line, coolly, coolly, coolly. So let's find a vector equation and the corresponding parametric equations of the line through 1, negative 2, 3 in the direction of 4i plus 5j minus 6k. Remember, I, j, and k are our unit vectors, so this is in unit vector form. Just a quick review, remember the vector I is 1, 0, 0. And then j is 0, 1, 0, and k is 0, 0, 1. So let's just start with the basic r equals a plus t b. And r represents any point on the line, x, y, and z. A is a point we know is on the line, yes, so that is the point 1, negative 2, 3, plus some parameter t, okay, some real number, represents any real number, and then we need the directional vector. Well, the vector 4i plus 5j minus 6k, that's our directional vector, and it's the vector 4, 5, negative 6. That is the direction that this line will be going, and that's all that goes right here. No big deal at all. So this is the vector equation right here, vector equation, I'll abbreviate equation. Once you have the vector equations, the parametric equations are easy. The parametric equations would be x equals 1 plus 4t, and I'm just going straight across here. X equals 1 plus t times 4 is 4t. Y equals negative 2 plus 5t. And finally, z equals 3 minus 6t. So there are my parametric equations. Okay, so right now it's just important that we are able to write and convert amongst parametric and vector equations. Okay. The non-uniqueness of the vector equation of a line, meaning it could take on many different forms, look very different, and we're still talking about the equation of a single line. So let's consider the line passing through the points 5, 4, and 7, 3. These points right here, and here's the line going through it. When writing the equation of a line, we could use either point to give the position vector of A, the position vector. In other words, we can use any known point on the line for the A in R equals A plus TB. Okay? A can be any point that we know. That's all that is saying. Really good stuff here. Okay? We could also use the direction vector 2, -1, but we could also use -2, 1. So this is what they're talking about. We could use either this for B or this for B. And where in the world does this come from? Well, remember, this is a vector getting from one point to another on the line. Let's take a look at 2, -1. If I start here and I went over 2 units, horizontal units, 5 plus 2 gets me to the 7, and the -1 I go down 1, then I end up at this point, 2, -1. That's the directional vector of that line. This, you can think of it as this vector right here. But that gives the direction of the line, right? And they have it written for us right here. We could also think of that as -2, 1 if I started here. Go to the left 2 and up 1. Okay? So we could have this vector right here, which they didn't put in here, they should have, -2, 1. It's this same vector just going in an opposite direction. So they're saying, okay, we could have this point or this point as the known point, and we could have 2, -1 or -2, 1 as the directional vector. Okay? So that's understandable, I think. So therefore, we could say, okay, the equation of this vector, or the equation of the line is x is equal to, and what they mean by x, that's the vector x, that's a little confusing. I'm going to rewrite that. I'm going to get rid of that and say xy, because that bold-faced x represents a vector. Same thing here. I'm going to get rid of that and write xy. I think that's a little confusing. So xy, this is my r, equals a, they chose this point, plus t times this directional vector, or xy equals, I'll use 7, 3, it's on the line, plus s times -2, 1. Notice we used a different t than an s here. Well, that's because they're different. We're using different points. This is because the parameters are clearly not the same. When t equals 0, we would have the point 5, 4. And when s equals 0, we would have the point 7, 3. And the relationship here is s equals 1 minus t. Well, where the heck does that come from? Well, that's not really that bad. That's just a matter of saying, like if I look right, oops, sorry. Here, I could say x equals 5 plus 2t. And right here, x equals 7, let's see, minus 2s. Okay, these x's are the same x. They are equal. So then I could set 5 plus 2t equal to 7 minus 2s. And that's where they got this relationship right here. So everything is very much interconnected, very, very logical. Okay. So one final example, and I'm going to shut up. Find parametric equations of the line through 2, -1, 4, and -1, 0, 2. So this is in 3 space. So, I'm not quite sure where this is. Maybe, I'll try and just do a quick sketch here. So x, y, z. So let's see, 2, -1, 4. So let's just say that's point A. And then -1, 0, 2. And that's point B. So I'm talking about a line in 3 space. Forgive the crudeness of my sketch. We're talking about the equation of this line. So I can use this point or this point to write the equation. Okay, either one of those points. Okay, so I'm thinking, okay, R equals A plus TB. right? So either this one or this one could be my A. Cool beans. But I need a directional vector. Well, I could use the directional vector AB, right? Because that vector is right here. Like that. And that is in the same direction as the line. Or I could use the vector BA. It doesn't matter. Since they're in order, A to B, I'm going to go ahead and use AB. I'm not going to use BA. And I get the vector AB. Let's see, -1 minus 2 is -3. 0 minus a -1 is a +1. And 2 minus 4 is a -2. Okay? So now I have my B. Life is fantastic. Okay? Now I would have x, y, z is equal to A. I can use either one of these, so this would be 2, -1, 4, right? Plus t times b, which I found to be the vector AB, -3, 1, -2. Now this is the vector equation. Okay, it asks for parametric. Well, the parametric equations, once you have vector, is easy. X equals 2 minus 3t, just going straight across. Y equals -1 plus t, t times 1 is t. And z equals 4 minus 2t. Okay? Now this would have looked very different. It would have been the same line, but it would have looked very different if I had chosen the point B. This here would have been -1, 0, and 2. And I could have also used the directional vector BA, the vector BA here. Any combination of those. So there's several different combinations, but they all would represent the same exact line. All right. Becker is out. See you next time.